Okay, hear me out. How about we nuke Neil Armstrong to space? Or maybe we just use a mass driver, a space tram, an insanely long lift, or let's just use a space fountain. Right? Today we have launch providers transporting massive payloads to orbit on a daily basis. Welcome to the new reality of spaceflight. But what if we didn't use rockets? There are many possible alternatives to get the job done. Some are theoretical and some look amazingly practical, while others are downright lunatic. Can we really get to space without a rocket? And if so, what would that even look like? My name is Felix, welcome to What About It. Let's dive right in and find some answers. After some rather extensive research, this is going to be my top 5 of all of them, ranked by craziness. Each concept in this video will get crazier than the one before it until we reach peak insanity. Alright, let's do this, brace for impact. We'll start with something that could come straight from the innocent fantasy of a child. Let's just throw things into space. The idea behind this is quite simple. If you just throw hard enough, you will reach space. Right? When you grow up, you realize that if you'd want to throw things into space, you'd need to throw really hard. One way to do this is to use a hypersonic space catapult. Do you know what this reminds me of? A centrifuge. They use something similar for astronaut training. A long arm is fixed on an axis in the center of a round room with the pilot's cabin on one side and a counterweight on the other. So far, so good. This machine makes practical use of a physical phenomenon. The linear speed of the cabin depends on both the rotation speed of the axis and the length of the arm. For each rotation of the axle, the cabin has to go the full circumference. This leads to very high speeds of the cabin, even at relatively low RPM at the axis. The idea to use a very similar contraption to hurl payload to space is not new. But these days, a company by the name of Spin Launch is working on making this idea a reality. Just like in the G-force trainers, we have a round room with a rotating arm connected to a central axis. But a few things are very different here. First of all, the operational spin launch is planned to have a diameter of 100 meters. NASA's astronaut centrifuge, in comparison, has a diameter of 17.7 meters. Small. Secondly, the room in which the system spins can be fully evacuated and thus will be the largest vacuum chamber ever constructed. The elimination of air resistance is vital to the concept. To reach space, the projectile is to reach a velocity of 12,875 kilometers per hour. That is a really hard throw. If not in a vacuum, at such a target velocity, the air in the chamber would cause enough friction to destroy the entire system. At the end of the spinning arm, constructed from carbon fiber composite materials for extra strength and light weight, is a mounting point for the orbital projectile. This rocket-shaped capsule is also made from carbon fiber, while the tip is made from super-hardened metal alloys capable of withstanding the incredible forces that come to play during a launch. We are talking around 60,000 Gs of centrifugal force right before the launch. Once the projectile with an estimated payload capacity of up to 200 kilograms has reached the predetermined velocity, it is released at just the right moment to leave the chamber through the exit tunnel, passing hyperspeed doors and finally breaking through a sealing membrane and shooting toward the sky. That sounds simple. The entire centrifuge will be built at a 35-degree angle to send the projectile on an orbital course. After reaching an altitude of about 60 kilometers, the capsule needs to activate its integrated cheat mechanism for the final push into orbit. It is a small rocket engine, without which even Spin Launch's lunatic spinning speed would not accelerate the projectile enough to reach full escape velocity. So far so good. Super fast spinning arm released just at the right moment and boom! We're headed to space. But would this actually work? The answer would be a careful yes. The science behind this project is solid. So solid that Spin Launch secured considerable investment and is already experimenting with smaller sized centrifuges. Orbital experimentation is targeted to start in 2026. Is it worth the research though? I think that's also a yes. If they build it and it ends up performing as they had planned, the per kilo cost of payload to orbit could be as low as 30% of the cost of a conventional rocket. As for its limitations, one problem is scalability. The bigger you build these centrifuges, the more exponentially the forces involved will grow. With today's materials, you cannot go much larger than the planned 100-meter diameter to assure safe operations. You know, boom! Another one is linked to immense forces. It is the amount of g-forces the projectile and the payload need to be able to endure. As mentioned, we are talking major forces here in the region of 60,000 Gs generated during the half-hour spin-up period. Half an hour. So the system is not an option for just any payload that needs to be delivered to orbit. How high is the crazy factor of spin launch? I rated a comforting 4 out of 10. This thing has the potential to become a reality in the not too distant future. Let's move up a tier and have a look at a concept known as StarTram. This is something known and beloved by sci-fi fans. StarTram is a mass driver. These machines offer a rocket and propellant-free method for launching payloads into space. While mass drivers have been a concept in speculative fiction since the late 19th century and various engineering designs have been proposed, significant technical challenges have hindered their development so far. But today we are a lot closer to mastering the required technology for such a mega project. Let's explore what this concept is all about and what it needs to be constructed, if ever. The first component is magnetic levitation, or maglev for short. This technology is already in use in public transportation today. It is the key to ultra-high-speed trains that can routinely run faster than 500 kilometers per hour. An improved version of maglev technology has been developed for Japan's next generation of Shinkansen trains. This SC maglev, or superconducting maglev, can deliver improved performance by utilizing superconducting magnets in its propulsion system. The entire train rests on a magnetic field. It doesn't touch anything, it floats. This L0 series prototype train holds the record for the fastest crewed rail vehicle, with a record speed of 603 kilometers per hour. And the speed can be improved further if you eliminate the main factor of resistance, air. Just like with spin launch, air resistance is the main enemy. In the case of the SpaceTram, this can be achieved by running the vehicles in a vacuum tube. This way, speeds of multiple thousands of kilometers per hour can be achieved. Very fast. While the method of propulsion is not that outlandish and very much possible to build with today's technology, the next element needed for StarTram is a whole different story. While the physics behind the concept is solid, its scale is a bit daunting. That is because we would need to build a constantly rising tube that extends over 100 kilometers in length. And that tube needs to rest on something, right? It can't just float in mid-air. Enter magnetically suspended superconducting cables. Sounds complicated, but it's actually straightforward. When opposing electric currents flow through two conductors, they experience a repulsive force that pushes them away from each other. Electromagnetism. This force increases with the current flowing through the conductors. And again, an emerging technology can help extend this principle's capabilities, and just like the launch vehicle's magnets, superconductivity is the key. These cables are conceptual for now, but they are already under development for superconducting power grids, and they can carry currents that go up hundreds of megaamps. Dr. James Powell and Dr. George Mays, the inventors of StarTram, say that a suspension system that has one superconducting cable on the ground and one suspended in mid-air above it can provide a levitating force of 4 tons per meter of StarTram guideway. And they could even generate this force if the two conductors are separated by a jaw-dropping 20 kilometers. So, having found a method to suspend the maglev track in its vacuum tube kilometers above the ground takes us straight to the next technological challenge. The floating track needs to be secured to stay in place. Under normal circumstances, the first thought would be to just tie it down using steel cables. Now, this is fine for the first few kilometers of track, but the higher it floats above the ground, the longer the cables get, and at the same time their weight increases too. This, unfortunately, is the cause of two problems. One is that at some point the weight of the cables will inevitably be larger than the levitating force the superconducting cables can provide. The other one is an even bigger problem for the next space launch concept I will explain in today's episode. Tethers have a breaking length. The braking length is the length a tether made from a certain material can reach before it will break under its own weight. The weight of a cable gets so large at some point that it rips itself apart. But there is good news for StarTram enthusiasts. Modern synthetic fibers can already deliver the capabilities to span the tens of kilometers needed for this launch system. The final technological ingredient needed to cook up a StarTram is called MHD, or magnetohydrodynamic pumps. Say what? In principle, this is not a new technology. It has been used for pumps, generators, and thrusters for many years. In its use case for StarTram, MHD will become the invisible barrier at the far end of the launch tube. I mean, somehow you need to seal it up while something passes through. This MHD window will allow ionized gases to be continually expelled from the tube. It's like a see-through vacuum pump. With this neat little trick, it is possible to keep a near vacuum and still have a tube with an open end for the vehicles to shoot out of. This, in short, is the concept for a more or less realistic mass driver. For a less crazy version of this, you could of course just accelerate a rocket with it. In this example, we have Rocket Lab's Electron endure a bit of a push, build a much shorter tube at 1 kilometer depth into the ground and use it to accelerate the rocket up to about 300 meters per second of velocity. That's fast. This animation is from Tim Dodd, the everyday astronaut, who we're collaborating with on this video. To learn more about the challenges and math behind such a project, check out his video as well. It's very much worth it. Tim, you rock. I always wanted to say that. Now it is time to ask our questions again. Is this a realistic technology? The surprising answer is yes, it is less far out than a first glance would make you believe. Is it worth the effort? If the system runs anywhere nearly as efficiently as its inventors think, we are looking at the capability of launching thousands of tons of payload per year into orbit for less than $40 per kilogram. That's nothing. Two proposed versions have been presented. One is a cargo-only version featuring a 100-kilometer-long underground tunnel with a bend upwards for the last kilometers that could be mounted to the side of a mountain. While this is much cheaper and easier to build than the levitating version, it could not be used to launch humans due to the immense G-forces coming into effect while changing direction upwards at the end. For crewed launches, StarTram would need the levitated tube version with a steady incline. What are the limitations of this technology? Let's keep aside the immense cost of constructing such a gigantic project. In that case, the main limitation lies in the maximum payload capacity of the individual launch vehicles, much like the fairings of rockets today, and their maximum lift capabilities. But such a system would compensate for these limitations with an unprecedented launch cadence. With enough electrical power, this system could launch multiple times per hour. And how high is the crazy factor for StarTram? This concept looks way more far-fetched than it is. I would not put it higher than a 5 of 10 on the crazy scale. Building it based on today's leading-edge technology is possible, with a budget high enough and a government or mega corporation willing to see this through. And from here on out, things are getting really crazy. If I told you that it was seriously considered to nuke a spacecraft to orbit, you might think that I am joking. This idea from the 1940s was explored to a great extent. The United States Air Force, DARPA, and NASA all conducted studies in the 1950s and 60s to find out if this next concept was viable. It was DARPA's predecessor, ARPA, that really got this idea going when they decided to fund and sponsor a program with the name Project Orion in July 1958. The leading scientists for Project Orion were Ted Taylor and Freeman Dyson. And yes, this is the Freeman Dyson who also theorized the Dyson sphere. Both were accomplished and very intelligent physicists, and especially in the early stages of development, high hopes were attached to this project. Wernher von Braun, who was convinced that Project Orion was the best option for a human exploration project to Mars, actively supported this. NASA's mission profile for this proposed a 125-day round-trip mission with a crew of 8. That is ridiculously fast. Even now, it feels like a utopian goal, as today's technology would not allow for the kind of speeds required to achieve such a short round-trip time. Alright, spill the beans. What is Project Orion all about? How does it work, and why could it have offered unmatched speeds over 65 years ago? The idea behind it is to use a form of propulsion that harnesses nuclear power. But we're not looking at nuclear batteries like they have been used on probes and satellites for decades. Project Orion wanted to use nuclear fission bombs to propel a spacecraft. Nukes, you know, the things that go boom. Seems simple enough. Detonate a nuclear bomb under the spacecraft and ride the shockwave upwards. Once the craft reaches the point at which it would start to fall back down, it releases and detonates another nuke from the bottom of the craft. Bloop. You'd repeat this until the craft reaches the desired speed. From today's point of view, we are inclined to discard this idea right away. No one in the right mind would seriously consider detonating dozens or even hundreds of nuclear bombs for a single spacecraft launch. But the physics behind Project Orion are sound. Preliminary testing was performed using conventional explosives. Using this method, the scientists were able to reach about 100 meters in altitude in a model test. The clever engineers even found a surprisingly elegant solution for the problem of the insanely abrupt acceleration inevitably tied to an explosion. The bottom of the Orion spacecraft, called the pusher plate, would be connected to the upper station via 2 sets of shock absorbers. They would then act as a buffer, temporarily storing some of the energy exerted onto the plate. The result would be a linear acceleration converted from the impulses of the detonating bombs. 2 ship sizes were envisioned for testing: interplanetary missions and advanced interplanetary missions. Each was planned to use as many as 800 bombs to reach a LEO of about 480 kilometers. The needed yield of each bomb ranged from 0.3 kilotons for the test article to 0.35 kilotons for the advanced interplanetary spacecraft. This largest version of the nuclear Orion spacecraft would be a true giant. Boasting a diameter of 56 meters with a height of 85 meters, it would have weighed a whopping 10,000 metric tons. That's a bit more than SpaceX's Starship, fully fueled. But even more impressive is that more than half of this weight would have been payload. On Starship, even if impressive, that's a lot less. 200 tons compared to more than 5,000. These numbers are wild, especially compared to today's technology. 6,100 tons to LEO or 5,700 tons to the moon. That is truly unmatched. And Project Orion was reaching out to even more distant targets. On a proposed return mission to Saturn, which was believed to be possible to do in just 3 years, the spacecraft could have still delivered a payload of 1,300 tons. That's mind-blowing. Here we have a case of a brilliant idea, but with dire consequences attached to it. NASA decided in 1959 that in the near term they would not opt for the nuclear propulsion option, but the research kept going. Project Orion was finally terminated in 1964 after the United States ratified the Partial Test Ban Treaty on nuclear fission bombs. So is this a realistic technology? By any means. It would work. All the needed technology is available, but the radioactive fallout created in a Project Orion spacecraft's launch is, let's say, not optimal. Yet, there is an application that still holds some potential for future space missions. You could use conventional rocket launches to bring all parts for a big interplanetary spacecraft into orbit and assemble the craft in space. Using conventional propulsion, this ship could exit Earth's orbit and only after leaving the vicinity of Earth and the Moon activate the atomic bomb drive. That's a cool name. Is it worth the effort? It can very much be worth the effort, as the potential power yield of nuclear detonation devices is unmatched by any other means of propulsion known to humankind at this point in time. What are the limitations of this technology? Radiation, obviously. Human passengers need to be protected from the nuclear explosions that propel the ship in space. But according to the project's scientific groundwork, this could be possible. This method would allow the use of heavy elements like lead shielding to keep the radiation at bay. So how high is the crazy factor of a Project Orion spacecraft? It is time to whip out a 6 out of 10. It is a very crazy idea, but still it has very realistic science backing it up. The possibilities are noteworthy, and the use of such technology in the future is possible. So, nuking a ship to space? What could possibly be even crazier? Oh, you bet I found some even crazier stuff. A sci-fi classic that has been featured in literature, games, and movies countless times. Something that seems so logical that many see it as an essential tool for spacefaring species that simply needs to be built sooner or later to ensure a transplanetary economy. Enter the space elevator. Going up, please. A space elevator envisions a cable extending from Earth's equator into space. A counterweight positioned far above geostationary orbit maintains the system's center of mass. The planet's rotation generates sufficient upward centrifugal force to counteract gravity, holding the cable upright and under tension. This structure would allow so-called climbers to transport cargo between Earth and space. An elegant and alluringly simple idea. No rocket engines, full reusability, very low energy consumption, likely the safest way of all to go to space. Right? Just push a button. And the idea behind it is not new either. Russian scientists described this concept back in the late 19th century. So how does this technical marvel work? Imagine you take a cable and anchor one end on the surface of our beautiful planet. To be precise, you do it somewhere along the equator. The other end is tied to a counterweight that is all the way out in space. If the counterweight is far enough away to raise the entire system's center of mass above the geostationary orbit altitude, enough upward centrifugal force is produced by the Earth's rotation to counter the downward gravity. This keeps the system stable with the cable tight and perfectly upright. But when something seems perfect and straightforward, there are often good reasons why it sounds too good to be true. In the case of the space elevator, the only problem is that there is no material we can produce today that would let us create the cable needed for this project. The braking length, as mentioned with the space tram, is an insurmountable problem at the moment. No material comes even close to not breaking under its own weight when you look at the length of cable required to construct a space elevator. What lengths are we even talking about, Felix? Can't be that much, right? Space is just 100 kilometers away. Here it comes. We are talking 100,000 kilometers. Why? Because the cable needs to be stationary and balanced. The system's center of mass needs to be in geostationary orbit where orbital speed and Earth rotation cancel each other out. Otherwise, the elevator wouldn't be above one point on the planet. Will this never be done? We can still figure it out. Scientists have an idea of a future material that could solve the space elevator's biggest problem. Imagine a ribbon made from carbon nanotubes that is thinner than a piece of paper and still has the strength to anchor the counterweight and allow climbers to go up and down the ribbon. Another study from 2019 proposes a potential process for manufacturing macro-scale single crystal graphene with an even higher specific strength than carbon nanotubes. Multiple companies are actively working on making space elevators a reality. So what do we think? Is this a realistic technology? The concept is scientifically sound. All we need is a material with the required specifications to create the 100,000 kilometer tether. And this is where the pitfall of so many futuristic ideas lies. They are completely feasible if you just have this one magical material with just the right attributes you need to fit the bill. Realistically, there are materials in an experimental state that might one day enable us to build this mega project. But there are no reliable estimates on when we can access these materials at scale. Is it worth the effort? Yes, it is just as good as it seems in movies. Once it is technically feasible, space elevators will be built. They'd be incredibly useful and make a great deal of sense all around. So what are the limitations of this technology? At the moment, science is not quite able to deliver all that is needed to build a space elevator. Once it is constructed, its potential is almost limitless. We can be very sure that if one is built, others will soon follow. How high is the crazy factor of a space elevator? Considering all that is involved, I need to give it an 8 out of 10. From today's vantage point, it is still very much sci-fi. It is a crazy idea and it will remain one until someday it hopefully becomes a reality. Now, my friends, it is time to present the craziest idea of these 5. Have you ever heard of a space fountain? This idea is a creative alternative to the space elevator. At its core lies a clever way of solving the need for a super material that does not buckle under its own weight, even when spanning tens of thousands of kilometers. The solution is to fire a constant stream of pellets up in the air. This is where the crazy factor slowly starts to build up. Of course, this idea seems outlandish at first, but bear with me. If you ever played with a water hose as a kid, you know that the water pressure sends the water upwards in an arc when you point the hose upward. You'll also feel that when you hold your hand in the stream of water, the water pressure pushes it away. Now imagine you apply this easy to grasp principle to create what is called an active structure. Such a structure cannot hold itself up and needs an active system to keep it standing. In our childhood memory, that's the running water hose. In the space fountain, this active system comes as a stream of particles, metal pellets to be precise, blasted toward the sky. And just like holding your hand into the stream of water, a so-called sky station is deflecting the stream and is thus kept in place by the force of the pellets. Et voila, it levitates. Crazy enough, we're not done yet. Because friction is the worst enemy in any such project, scientists have found a clever way to do this frictionless. The solution comes in the form of permanent magnets. Such magnets in the shape of an arc deflect the metal pellets and at the same time they are attracted to the pellets, keeping the station in place like a magnet stuck to a piece of metal. The endless stream of pellets goes up straight, is forced into a curve by the magnets, and is then sent straight down again on the other side. Reaching a bottom station, it can be deflected back up in much the same way, and by the means of magnetic acceleration, additional force can be applied to keep the particle speed steady. Most of the energy that is used to shoot up the pellets is recuperated when they fall back to Earth, thanks to gravity. Convenient. In order to eliminate as much friction as possible, the stream would have to travel inside a vacuum tube, at least for the lower parts of the atmosphere where air resistance is strongest. Theoretically, a space fountain can run incredibly efficient as long as you eliminate most of the friction. So now we have a stable floating platform up in the sky. But how do you get anything up there, let alone from there to outer space? Maglev is the answer one more time. The steady stream of metal can act just like a fixed metal rail for a vertical maglev transporter. The fountain is just there to provide a structure to travel along. Once on the upper platform, payload can be loaded onto rocket-propelled transporters to reach the desired orbit, skipping the atmosphere and thus making spaceflight much more efficient. Alright, super accelerated metal pellet stream. How realistic is a space fountain? While at first glance it feels impossible, the physics at the base of the system is proven and well known. I'd argue it is even more realistic to build, as in principle we have all the needed materials. It can be built at any desired height, as its support comes solely from the ground-based station, and there is no need for a counterweight as on the space elevator. Therefore, such technology could be pioneered in the construction of towers that break the multi-kilometer mark. It could even be used to build floating buildings. So would it be worth the effort? We have another yes here. While it surely is a megastructure and those are always hard to build, the space fountain has an amazing efficiency when it comes to power consumption. With a lot less effort needed to be constructed, we will likely see space fountains before space elevators are introduced. What are the limitations of this technology? There are a lot of details about space fountains that I did not go into in depth. The most important one is the need for a permanent, uninterrupted power supply and ways to build redundancies into the system. A total loss of power would be catastrophic, as it would lead to an inevitable loss of the upper station, which would come crashing down instantly. Tallest freefall tower ever. Also, you'd still need means to accelerate your space transporter from the upper platform, especially horizontally, to reach a steady orbit. We'd likely use rockets to launch from the top station, as they can launch exerting downward pressure only and then change their trajectory into a stable orbit without pushing the platform sideways. Yeah, imagine that. So how high is the crazy factor of a space fountain? It was a close race between the space fountain and the space elevator. While the elevator needs a still-to-be-invented material to be built, the space fountain feels as counterintuitive as it gets. Hanging something from a super-accelerated stream of metal pellets feels almost impossible and more like a thing straight out of science fiction. Even with it being scientifically sound, I have to give the space fountain a 10 out of 10 on the crazy scale. We have a winner. Let me know in the comments what your favorite was and if you know of any other outright crazy ideas to get to space. If I get enough suggestions, I might just do a part 2 of this. That's it for today. Remember to smash that like button, subscribe for more. This is what fuels the algorithm, and this is how you can help us for free. Check out our epic shirts in your favorite Space Nerd store. A new Raptor design and our Mechazilla shirt are both up. Link is in the description and in the card you should see now. And if you want to learn about SpaceX's Raptor engine and how it is completely revolutionizing spaceflight, watch this video next to continue your journey. Thank you very much for watching, and I'll see you again in the next episode.